Welcome back to our video module on quantum mechanics. Thus far, we've spent a little bit of time exploring some of the physical phenomenon that relate to quantum mechanics, and today we're going to explore a little bit of the probability that will help us as we dig deeper into quantum mechanics. Today, we're going to cover the mean and the standard deviation for both discrete and continuous distributions. Now, if you've already seen this stuff before, I'd encourage you to still watch the video because I include some subtleties that are important as we use it in quantum mechanics. So on the right, I've drawn out a histogram that reflects the scores that a class of 10 got on a quiz, and the quiz is out of 10 points. You see that we have four students got 10s, 1, 2, 3, 4, 2 got 9s, and so forth. Now, of course, the obvious thing that you've probably been doing all your life is identify what is the mean. Well, we take whatever the score is, we'll call it X, and we multiply it by the number of students who got that score, divide it by the total number, and that equals your mean, which in this case is 8. Look at the score and the number of people who got that score for every score, summed over all data. Here I've used Einstein notation in the numerator. Now, what does that mean? Does that mean any students got an 8? Well, no, not at all. I mean, look at the graph. There's nothing here. At 8, no one got an 8. What it means is that if we were to take this quiz over and over and over again, the type of score that one would expect would be an 8. And so what we do is we call this the expectation value. This is the average. This is the score that if we were to do this over and over again, the center of all of the numbers. It does not mean that it's a score that somebody got, or maybe even a possible score.
Of course, our analogy isn't perfect because the distribution I've written here was a one-time experience, and if we want to know how things function time and time and time again, we would use a full population distribution.
The way we can talk about this in math terms is we'll put brackets around that, and we'll say that x equals an 8. Using this notation, we also have a definition for the standard deviation, which is a measure of the spread of a system. And we know that that is the average of x squared, or the expectation value of x squared, minus the expectation of x squared.
And I should note here that the equation written is simply a more convenient form of the RMS deviation from the mean.
And in this case, the expectation value of x squared, we would write, go ahead and borrow from this right here, which really equals the expectation of x. We would say it's equal to x squared, the score squared times n divided by the total number,
summed across all n's.
Now that's how we under discrete distributions, but what if we look at continuous distributions? So what I've done is I've drawn out some curve, rho of x, that tells you the distribution of scores of x. And we're basically going to follow the same format as we had up here. In green, if we wanted to know the expectation value of x, we would take a look at the score. We'll say this score times n, the number of students, which in this case is going to be the value of rho of x, divided by the total area under the curve, which relates to n, or the total number of students. So if we wanted to write that, because we're looking at a continuous distribution, it's going to be x times rho of x, d of x, divided by the whole area under the curve, which is simply integral of rho x dx. This equation tells us the expected value of x, and we can actually think of it, we'll say in orange here, it's probably somewhere around here. You can think of it as a weighted average. So in summary, we have a relatively simple equation for identifying the mean, and we have a way of understanding what that mean actually is defined as an expectation value, and we've looked at it for both discrete probability distributions as well as continuous probability distributions. Finally, we've seen how that expectation value of x and the expectation value of x squared relate to the standard deviation, or the measure of the spread of the data. Join us next time as we look at how this relates to probability.